All right, first question on the practice exam 6. Is BOH3 more soluble in CH3CH2OH or C6H6? All you have to do is like dissolves like. All right, and so when you see OH, you have hydrogen bonding, and when you see OH, you have hydrogen bonding, and like dissolves like. And so your CH3CH2OH would dissolve your BOH3. It is much more soluble in that than it would be in C6H6. Number 2 says solubility of CO2 is 0.161 grams per 100 mils of water at 20 degrees Celsius in 1 atmosphere. Pepsi is carbonated at 5.50 atmospheres. So calculate the solubility in Pepsi. All right, so the solubility of CO2. So we are pressuring the gas, we're pushing the gas into the liquid, Pepsi, and so you're going to have an increased solubility. All right, and so your solubility is equal to your constant, Henry's law constant, times your pressure. All right, and so you can do S1 over P1 is S2 over P2. So we know that the solubility 1 is 0.161 grams per 100 mils of water. We know pressure 1 is 1 atmosphere. We know solubility 2 is our question. We know that pressure 2 is 5.50 atmospheres. And so you simply multiply both sides by 5.50, and you have your answer. You increase the pressure, you increase the solubility of a gas in a liquid. So 0.161 times 5.5, 0.886. So solubility of CO2 is 0.886 grams per 100 mils. All right, and then to calculate Henry's law constant, you simply take the K sub H and divide both sides by P, so you get S over P. It doesn't matter which set you take, it's a constant. All right, so if you want to take your newly formed solubility divided by the 5.5, or the much easier 0.161 grams per 100 mils over 1 atmosphere. All right, so then you have your answer. The answer for K sub H is 0.161 grams per 100 mils of water times atmospheres. All right, so the denominator now has atmospheres. It's not exactly the same as this. We had to divide by 1 atmosphere. And so that is your Henry's law constant. All right, number 3. 3 has A through L. How would you make 145 grams of 2.5% Ki? A much easier question would be, how do you make 2.50% Ki? Well, you assume a 100-gram sample. When you see percent, it is a mass percent, unless it says otherwise. It could be a volume, it could be a mass volume. If it doesn't state, it's a mass percent. All right, so if you assume a 100-gram sample, that means you have 2.50 grams of Ki, and you have 97.5 grams of water, which means you have 100 grams of solution. So if you take 100 grams of that solution, 2.50 grams is Ki, 97.50 grams is water. All right, so if we wanted to make the 2.50% Ki, you simply take 2.50 grams of Ki, 97.5 grams of water, and you dissolve the Ki in that water, and you have your solution. It was more specific. It wants 145 grams of this solution. All right, and so the way I do it is I like to set up a ratio. Lots of different ways you can do it. I know that I needed 2.50 grams of Ki to make 100 grams of this solution. What I want to know is how many grams of Ki do I need to make 145 grams of this solution? All right, and so then you just cross multiply and divide. So you have your 2.50 times 145 divided by 100. And you get 3.625 grams. All right, so in sig figs, it should be 3 sig figs, 3.63. I'm not going to take off for sig figs unless it is ridiculous. But if it's supposed to be 3 and you gave 4, that is fine. Depending on the balance that you're using, if you're using a 4 decimal place balance, this works great. If you only have a 2 decimal place balance, no need to give that third decimal. All right, but if you say, how do you make it? Well, you make it 3.625 grams Ki. That is not how you make anything. That is an amount of Ki. All right, so we know that we have to have 145 grams total. So we need 141.375 grams of water. And that will give us our 145 grams of solution. So if we're doing 3 sig figs, which we probably should be doing, everything was given to 3 sig figs. So you would dissolve 3.6, now I'm going to go with the whole thing, 625 grams of Ki in 141.375 grams of water. All right, so that's more sig figs than you need. So you could say 3.63 grams of Ki in 141 grams of water, and that would be fine. It's not great, but that would be 3 sig figs and 3 sig figs, and that would be fine. All right, so this is a percent. This is not a molarity. We're not diluting to some mark. It is a mass percent. You put in that mass, you put in that mass, you mix it together, you have your solution. All right, so part B. What mass of 2.5% Ki is needed to obtain 258 milligrams of Ki? All right, so what mass of 2.50% Ki is needed to obtain 258 milligrams of Ki? All right, so we have our amount of Ki that we want, and we'll put it in grams. So convert this into grams. We need 0.258 grams of Ki. So what we know is if we wanted 2.50 grams of Ki, we would need 100 grams of solution. If we wanted 0.258 grams of Ki, we would need what amount of solution? So again, you cross multiply and divide. So you take your 100 times the 0.258 and then divide it by 2.5. And you get 10.32. Here, I'm going to go with the correct sig figs, 10.3 grams of 2.50% Ki. So if you took 10.3 grams of 2.50% Ki, that would give you the 258 milligrams of your Ki. Part C. Calculate the molality of 2.50% Ki. All right, so this could be an extremely hard question because, well, it's impossible if you don't know the units. You must know the units, the specific units for molality. If you know them, then the problem is much, much easier. This is moles of solute. In this case, solute is Ki, divided by kilograms of solvent. In this case, the solvent is water. All right, so now we go back and we have our 100-gram sample. And we remember our 100-gram sample has 2.50 grams of Ki, and it has 97.50 grams of water. All right, so very easy to get moles of Ki. You just take the mass of Ki divided by the molar mass of Ki, which is 166 off the periodic table. K is 23, I is 127. You add those up, you get 166. Is that right? No, that's 39. That's not sodium. It is 39 and 127 because that would add up to 166. And then water, we just have to convert that into kilograms by dividing by 1,000 to get us into kilograms. So you take your mass divided by your molar mass, 2.50, divided by 166 to 3 sig figs, you got 0.151 moles of Ki. Kilograms, you don't have to push the buttons. It's 0.09750 kilograms. All right, so now you've got your moles of your Ki, 0.151 moles Ki. Now you have your kilograms of water. It is 0.09750 kilograms. You divide those two things. And to 3 sig figs, you got 0.154 molal. All right, if you know the units of molality, it is a matter of converting grams into moles and grams into kilograms and dividing the numbers. If you don't know the units of molality, then that is an impossible question. Part D, calculate the mole fraction of Ki. All right, again, if you don't know what mole fraction is, impossible to get it right. Mole fraction. All right, so you need to know that you're going to need moles of your Ki, and then you're going to divide that by your moles of Ki plus the moles of water. All right, so it's a mole fraction. Moles of the Ki divided by the moles of the solution, which is the solute Ki and the solvent H2O. We already have the moles of Ki. We calculated it right above here, 0.151. All right, we didn't convert our 97.50 grams of water into moles. We put it into kilograms because that's what we needed for molality. Now we need it in moles. Divide by the molar mass, 18.02. So when you take your mass of water, 97.5, divided by your 18.02 to 3 sig figs, you get 5.41. So that is equal to 5.41 moles of water. All right. So you take your 0.151 divided by the addition of 0.151 and 5.41, and you get your mole fraction, which is 0.0272. All right, so that is your mole fraction of Ki, which means that 0.9728 is your mole fraction of the water. Because the fractions always add up to 1. But it didn't ask for the mole fraction of water, but if it did, that's how you would get it. Mole fractions add up to 1. Percentages add up to 100. All right. Part E. Calculate the boiling point of 2.50% Ki. So now we want the boiling point. And that is going to be delta T sub B is equal to I K B C sub M. All right, so we are talking about Ki. Ki has K plus and I minus. So the first thing you need to know about Ki is that you have two ions in solution. All right, and so you have your 2. Kb, you look it up, 0.512 degrees Celsius per molal. That will be given on the test. And the molal solution, we have it circled right above. In part C, we calculated it is 0.154 molal, 0.154. The molals cancel, and this gives us our delta T sub B. Which is 0.158. And that is an answer on the test. That is the wrong answer on the test because the question in E says, what is the boiling point? So you have to know that your delta T sub B is a boiling point elevation, not an actual boiling point. It's how much the boiling point goes up. And so your boiling point is 100.158 degrees Celsius. So you have to know it's a boiling point elevation. It was water. Now we put in some Ki, and the boiling point is going to go above 100. How much above 100? You calculate it with your delta T sub B. That is your boiling point elevation. All right. F is to calculate the freezing point. Delta T sub F is equal to I Kf C sub M. Everything's the same except for this is the constant for freezing. So delta T sub F, you have Ki, 2 ions in solution. Kf, you look it up, 1.86 degrees Celsius per molal. Molality was calculated in part C. It is 0.154 molal. When you multiply those together, you get 0.573. All right, now this one is close to an actual freezing point. That's a very low temperature, where if you said the boiling point was 0.158 degrees Celsius, that's a ridiculous answer. To say the freezing point is 0.573 is not a ridiculous answer. It's the wrong answer because you have a freezing point depression. That is how much it goes down. Water, of course, freezes at 0 degrees Celsius, and now it freezes 0.573 degrees Celsius less than that, and so your temperature of freezing for this solution is negative 0.573 degrees Celsius, because that's how much it went down from its normal freezing point of 0. G says the mass of 10 mils. All right, so the mass of 10 mils of my 2.50% Ki was determined in the lab to be 1.1 gram, 11.1 grams. Calculate the density. All right, so remember, density is the mass over the volume. All right, now that's not good enough. You need to know density is mass of solution over the volume of solution. All right, so we didn't take 10 mils of water. We didn't take 10 mils of Ki. We took 10 mils of the 2.50% Ki solution. We didn't weigh just the Ki part. We didn't weigh just the water part. We weighed the 2.5% Ki solution. So density is always mass of solution divided by volume of solution. All right, so you simply have the density is the 11.1 gram divided by the 10.0 mils. and you don't need a calculator for that. Your density is 1.10 grams per milliliter. All right, and we're going to need that for H, which is going to be the hardest question so far, and that is to calculate the molarity. All right, so you have to calculate the molarity. All right, so now again, moles per liter will not get you the answer. All right, moles of solute. So you have to know that Ki is the solute. We've already calculated moles of Ki a bunch of times. So we already have that one. And then liters of solution. And that's why we did density. That's the only place where we have a volume of the solution. All right, so to find the volume of solution, we need to first find the mass of solution. So we have moles. We have, all right, so we have our 2.50 grams of Ki. We have our 97.50 grams of H2O. We have our 100 grams of solution. All right, so I would rewrite that as many times as you need to rewrite that. When you have a 2.50% of Ki, that is what you have. So we already took the 2.50 grams and converted it to moles by dividing it by 166. And we got the 0.0151 moles. So we have our 0.151 moles of Ki. All right. And we have our mass of solution, but we don't want the mass of solution. We want the volume of solution. And so we have 100 grams of solution. And we know that we have a density of 1.10 grams of solution per milliliter of solution. And now all we have to do is get rid of milliliters and get liters, and that is 1 times 10 to the minus 3. And we have our volume in liters. So we take the 100 divided by the 1.10, and then times the 1 times 10 to the minus 3. And we get 0.0909. To 3 significant figures, 0.0909 liters. So we take our 0.151 and divide by that, and we get our molarity. And so the molarity, when you take and divide that by that, is a 1.66 molar. All right, now that we have the molarity, we can calculate the osmotic pressure at 20 degrees Celsius. Because osmotic pressure is pi, that is your osmotic pressure, is equal to IMRT. And so we have I, which is 2 because it's Ki, potassium ion, iodide ion, M, 1.66 moles per liter, we just calculated. R is a constant given. We have to use the one that's going to give us a pressure, and that is the 0.08206 liter atmospheres per mole Kelvin. And then at 20 degrees Celsius, that is 293 Kelvin. Always in Kelvin, never in Celsius. And so the Kelvin cancels the Kelvin, the moles cancel the moles, the liters cancel the liters, and we have our osmotic pressure in atmospheres. And that is 79.9 atmospheres. That is the osmotic pressure of this solution. All right, calculate the vapor pressure of pure water at 20 degrees Celsius. All right, so this one you have to know the normal boiling point. So you have 100 degrees Celsius. Normal means 1 atmosphere. So that is your normal boiling point. You also need your delta H of vaporization. And that will also be given, and that is 40.7 kilojoules per mole. And now you use the Clausius-Clapeyron equation. ln P2 over P1 is equal to delta H vaporization over R, 1 over T1 minus 1 over T2, and you have everything except for a pressure 2. All right, so the higher the temperature, the higher the vapor pressure. All right, so the vapor pressure right now is 1 atmosphere at 100. It's going to be much less than that because we are at a much lower 20 degrees Celsius. All right, so the ln of P2 over 1 atmosphere is equal to 40.7 times 10 to the third joules per mole. I got rid of the kilojoules. K is times 10 to the third, so I just put instead of K, 10 to the third. That means I have to have the 8.314 joules per mole Kelvin. Because if you use the other one, you will not get the units to cancel. You must have the R value that has joules per mole in the units. 1 over T1. All right, so our T1 is 100 degrees Celsius. Do not put in 100 degrees Celsius. Always in Kelvin. Add 273. So that's 373 Kelvin. Minus 1 over T2. We are at 20 degrees Celsius. Never put in Celsius. That is a 293 Kelvin. All right, so we'll do the parentheses first. And if you do the parentheses first, this is a negative 7.32 times 10 to the minus 4. All right, so times the 40.7 times 10 to the third. And divide that by 8.314. And you get that the ln of P2 is equal to negative 3.5834. All right, then you push your inverse ln, your e to the x button, and you get your pressure 2 in atmospheres. So pressure 2 in atmospheres is 0.0278. It doesn't say you have to be in millimeters of mercury, but I always, when I do vapor pressures, want them in millimeters of mercury. So multiply that by 760 to get the 21.1 millimeters of mercury. All right, if it doesn't say, of course, this is exactly the same answer in atmospheres. There's the answer in millimeters of mercury. So make sure you know how to convert from atmospheres to millimeters of mercury. Many times it is asked for pressure in millimeters of mercury. All right. Calculate the vapor pressure at 20 degrees Celsius. So now we have the vapor pressure of the 2.5% of the Ki. All right. And then calculate the vapor pressure lowering. KL I'm going to do together, okay, because my favorite equation to use is the vapor pressure lowering is equal to I mole fraction of your Ki times the pressure of your pure water. All right, so that is your vapor pressure lowering is the I value for Ki is 2. The mole fraction of Ki, if we scroll up, we already did the mole fraction of Ki, and the mole fraction of Ki is 0.0272. And then the pressure of pure water at 20 degrees Celsius is right there. It is the vapor pressure of water, 21.1 millimeters of mercury. So when we multiply those together, we get 1.15. All right, so that is the answer to L. L says calculate the vapor pressure lowering. That is the vapor pressure lowering at the 20 degrees Celsius. All right, and of course, for K, if I started with 21.1 millimeters of mercury and it lowered by 1.15, then my vapor pressure is 19.95. All right, which if you were then going to round it, it would round to 20.0 millimeters of mercury to 368. So that is the pressure of your solution. The vapor pressure of the solution is 20.0 because it had a vapor pressure lowering of 1.15 millimeters of mercury. All right, that is number 3. Number 4. All right, it's another how would you make. All right, this time we're going to make a molar solution. We want to make 2 liters of 2.50 molar Ki. All right, so again, you need to know the units for molarity. So you have 2.50 moles of Ki per liter of solution. We want to make 2 liters of solution. All right, and we're going to have to weigh out our Ki, which has a molar mass of 166 grams per mole. And so the liters of the solution cancel, the moles of the Ki cancel, and now we know how much Ki that we need to weigh out. We need to weigh out 830 grams. All right, so that does not answer the question. The question was, how do you make this? And 830 grams is just a big hunk of solid. That is not how you make it. So how you would make it is you would dissolve 830 grams of Ki in 1 liter of water, then dilute to 2.000 liters with water. So you have to dissolve it 830 grams of Ki is going to take up a lot of volume. You want to make sure it doesn't go over the 2 liters. All right, so you're going to dissolve it in 1 liter of water, and then you're going to add water until you get up to the 2 liter mark. And now you have 2 liters of solution, water and the solute. If you add 830 grams to 2 liters of water, you're going to be way over 2 liters of solution. 830 grams is a giant amount of Ki. The volume is going to go above the 2 liter mark. So make sure you dissolve it in a much smaller amount of water, and then you dilute to the mark. You cannot go over the volume. It's impossible, well, not impossible, very difficult to take things out. You're going to have to boil it or whatever. Much easier to add water. All right, part B. What volume of 2.50 molar Ki is needed to obtain 20 grams of Ki? You can set up a ratio from the last equation, but this is the way that it is done. You take your 2.5, you take your 20 grams of Ki, and you divide by the molar mass, which is 166 grams per mole. All right, and so this is how many moles of Ki that we need. And we know that the molarity is 2.50 moles per liter of solution. And so the moles cancel, and now you have a volume of the solution. So you take your 20 divided by your 166, that's your moles, and then we divide that by 2.5. And then we have our answer in liters. So let's then convert to milliliters. And you get 48.2 milliliters. All right, so if you take 42.8 milliliters, 48.2 milliliters of this 2.50 molar Ki, that will contain 20 grams of Ki. The freezing point of H2C2O4, temperature of freezing, is negative 1.0 degrees Celsius. Calculate the molality. So now we have a freezing point depression problem. And so we have our delta T sub F is equal to I Kf C sub M. All right, our delta T sub F, we know that it is 1.8. The freezing point would have been 0. It is negative 1.80 because the freezing point depression brought it down by 1.80. The I value is interesting. This is an acid. When we did chapter 4, did we break it up? Did we not break it up? We had our 6 strong acids. This was not one of them. So this is a weak acid, and remember, if you have a weak acid, it all stays together. When it all stays together, you have one molecule in solution. This does not break up. The only acids that break up are the 6 strong acids. You look up your Kf, 1.86. And then you have your C sub M, which is the question. So divide both sides by 1.86. And you get your molality, 0.968. All right, part B, calculate the boiling point. All right, so your boiling point elevation is your I value 1, Kb, look it up, 0.512. We just calculated the molality, 0.968. and you get 0.495. All right, and so the boiling point is not 0.495 degrees Celsius. Your boiling point elevation is 0.495. The boiling point is 100.495. It's a boiling point elevation. Boiling point of water is 100. It's going up by 0.495. So the boiling point is 100.495. Calculate the mole fraction of this weak acid is part C. All right, so again, we need to have moles of the weak acid divided by the moles of the weak acid and the moles of water. All right, and we have a 0.968 molal, 0.968 moles of the acid per kilogram of water. And so if you know that, then the question is very simple, because the moles of your weak acid, you already have it. It's 0.968. It's 0.968. And to get to the moles of water, we have 1,000 grams, and divide that by the molar mass. And that is 55.5 moles of water. So that just goes here, 55.5 moles of water. And that gives you a 0.0171. That is your mole fraction of your H2C2O4. All right, so then the mole fraction of water, if they ask for it, they do not, but it would be 0.9829. So they add up to 1 when you add up those mole fractions. Go down to number 7. All right, so this is a volume of the cube, which is equal to A cubed, a cube, the same length, width, height, length times width times height. That is all the same, so we're calling that A, and that is mammal DNA. All right, and so where your L is equal to 1, 2, or 4. If it is simple, it is 1. If it is body, it is 2. If it is face, it is 4. And these are atoms in the cube. All right, and so the question is, what is it simple body or face? So we're solving for L. So they give us the A value. The A value is 4.079 angstroms. I will immediately convert that into centimeters. 4.079 times 10 to the minus 8 centimeters. You should be very familiar with the lengths will always be times 10 to the minus 8 centimeters. All right. And you need that because the density is 19.3 grams per centimeter cubed. This has to match this. If this is centimeters cubed, this has to be centimeters. If you want that to be angstroms, then you have to change your density to grams per angstroms cubed. I prefer to convert my length and not my density. All right, and then they give you the molar mass. Molar mass 197. And so all you have to do is put in the numbers they give you. You had to convert the angstroms into centimeters. All right, but you got your 4.079 times 10 to the minus 8 centimeters. You're going to cube that. Your molar mass is 197. The L value is what we're solving for. The density is 19.3. And Avogadro's number is 6.022 times 10 to the 23rd. And so you multiply both sides. Well, first you're going to take your 4.079 times 10 to the negative 8, and you're going to raise that to the third. And if you're doing that correctly, you get 6.787 times 10 to the negative 23rd. And now we're going to multiply both sides by 19.3. Then we're going to multiply both sides by Avogadro's number. And then finally, we divide both sides by the molar mass, which is 197. And when you do that, you get L is equal to 4.00. All right, and so that tells you that it is face centered. All right. Then you have to look on your chart, and you're going to have 3 radius is equal to A's, or A's are equal to radiuses. So for your simple, your radius, so 2r is equal to a for simple. And then the Pythagorean's theorem, a squared plus a squared is equal to 4r squared. 2a squared is equal to 16r squared. A squared is equal to 8r squared. And so a is equal to 2 square root of 2 r. All right, so this one is for face centered. All right, so in the second question, it says, what's the radius? Well, they give us the A value. It is 4.079, and that is equal to 2 times the square root of 2 times your radius. So you take your 4.079 divided by 2, and then divide it by the square root of 2, and you get 1.442 angstroms. And if you want that in centimeters, you have 1.442 times 10 to the minus 8 centimeters. All right, then when you want the volume of an atom is a sphere. And that is 4/3 pi r cubed. So you take that number and cube it times pi times 4 divided by 3. And that is 12.6. And I left them in angstroms, so it is 12.6 angstroms cubed for the volume of a gold atom. All right, we will do the space occupied tomorrow. We'll do it for all 3, the simple, the body, and the face, and we'll finish number 6. And if you have any questions, bring them or email them, and we can work on those as well. And there will be something on Friday. I'm going to send it out today. This Friday.
This Friday.